Very happy to have Grisha here today with us about equivariant automorphisms of the Fox structure.
Yeah, thank you to the organizers for allowing me to present in this seminar. Okay, so let me start with a plan. Today's talk. So the first part would be what is simplicial, and simplicial not in any sort of homotopical sense, dark variety, or just the Cox presentation. Dark varieties. The next part would be the Cox's description of automorphism groups of dark varieties. Well, it will be a sketch anyways. The third part would be about the notion of a generalized fan. And there are Cox rings. Part 4 will be about equivariant automorphisms on the Cox construction of a generalized fan. And finally, hopefully we'll see some applications. To automorphism groups of complex manifolds. Okay, so that's the plan. And I could say that I think my talk would be so elementary that there is no need to separate it into two parts. Both of them are hopefully extremely simple in terms of like the theoretical background. Okay, so let's start with part 1. What is a simplicial dark variety? So let me first give you an example. So our favorite example is, of course, CPM. We know that this is a dark variety, and I want to give a very specific presentation of CPM. So you can present it as a quotient of the affine space without the origin, modulo the diagonal group action. So we have the multiplicative group of complex numbers, and we have this sort of algebraic Hopf vibration. And of course, well, not of course, but maybe you have seen a picture of the fan of CPM. I'm not claiming that you should have seen it, but maybe you've seen it. And maybe you've also seen that this corresponds to the n simplex. So in the next few minutes, I will try to explain why that is. So yeah, so let's sort of look at this picture. Let's ask ourselves, can we generalize it. So we want sort of a family of examples that are exactly like CPN, but different. So here we have some open subset of the affine space, and we have an action of a subgroup of the large torus that acts on the entire affine space. So a sort of very natural way to generalize it is to just ask, well, can we have some other open subsets of the affine space that are also invariant under actions of groups like this? And what are the quotients? So consider C to the power of M, or this, but I'm not going to write it like this. Then we have the action of the m-dimensional torus on this affine space, and we can ask what are subvarieties, quasi-affine subvarieties of CM, which are invariant with respect to this action. And essentially, by answering this question, we obtain this sort of combinatorial classification of dark varieties. So now let me give you some combinatorial definitions that would be necessary to perform this classification. So let S be a finite set. A simplicial complex on S is a collection of subsets of S, collection K of subsets of S, such that for any sigma in K, for any tau, which is a subset of sigma, tau also belongs to K. So we can define two auxiliary notions here. So first of all, colloquially, these elements of K are called faces of K. And if S and S is not in any face, it's called ghost vertex. Because in principle, no one asked us to cover the entirety of S with faces of K. Okay, so now we have this notion of a simplicial complex, and I'm going to associate to it a quasi-affine subvariety of CM built from this combinatorial data. So K simplicial complex on this. Then we have the following quasi-affine subvariety. So we take the union over all faces of K of CS minus hyperplanes, which are determined by complements of faces in K. So in particular, let's consider an example. So an example of this would be K on the set of natural numbers from 0 to n, where sigma belongs to K if and only if the cardinality of sigma is equal to n. So this is the n simplex, and the corresponding quasi-affine subvariety is just Cn plus 1 without the origin. So we throw out sort of hyperplanes given by a single coordinate equation, then we take the union of all such things, and the only non-covered point that remains is the origin. Okay. Any questions about this?
Sorry, you just say how you get this begin.
How I do what?
How you get PN. You're saying this U of K in this example is literally PN.
No, I'm saying it's Cn+1 without the origin.
Oh,
Sorry, what is your simplicial complex here?
It's this thing. So sigma belongs to K. Well,
That doesn't fit your definition.
yeah, exactly. If the cardinality of sigma is equal to n, and then we generate everything by these guys.
So it's all things of cardinality smaller than or equal to.
Yeah, yeah. So I guess yeah, thank you. Yeah, but also you can phrase it that way. Anyhow, this is just the simplex.
Yeah.
And the point is that when we perform this operation, we get the entirety of the affine space without the origin. Okay. So this sort of gives us a recipe how to get quasi-affine subvarieties of the affine space. Like we have this combinatorial datum of a simplicial complex, and from that we build like a quasi-affine subvariety. But this is not the only ingredient that we have that gives us CPN. We also need a group action. So how do we get a group action from this? Well, for this we'll need some additional combinatorial structure. So want a group action like the C star action on the affine space. So we need the notion of a fan. So a cone in our vector space V is just a Simon group like this. You take a bunch of vectors, you generate the same group. Then a cone.
So you want V1 through Vk to be linearly independent?
No,
Okay.
not
so it could
necessarily.
have,
I mean,
it doesn't have to be discrete.
well,
Oh, never mind.
Yeah, it doesn't matter. Like you can add more vectors, it will be the same thing.
But in particular, you can have like a vector and it's negative.
Yeah, I'm going to say something about this in a moment. A cone is called strongly convex. It doesn't contain lines. So that's an additional condition of the cone to not have a vector in this parameter. And a cone is simplicial if it's generated by a part of a basis. So two pictures. So this is a strongly convex cone. This is not. This thing is a simplicial cone. And if you add one more generator like this, then this is not a simplicial cone because you have too many generators. Yeah, and I think that's it. These are two additional geometric properties of cones that we can require. So now definition and embedded fan or just a fan is a collection of strongly convex cones such that first for any two cones in sigma, their intersection is also in sigma. And the second thing is that for any cone in sigma, if you have a hyperplane and you intersect C with this hyperplane, it's also in sigma.
So is that for any hyperplane at all?
I mean, yeah, because it's, I mean, it should be like a linear hyperplane.
Yeah.
But yeah. Or I mean, you can require something slightly weaker, but it's pointless. Okay. So one more definition. So here we have the sort of a bunch of convex subsets of a vector space. So we can define what is called a marked fan or a marked embedded fan. Is a fan sigma together with a choice of generators for one-dimensional cones, which are also often called rays. So we choose a vector on each ray of our fan. And then we also say that the fan is simplicial if each cone is simplicial. And a fan is complete if the union of cones in sigma cover the entire vector space. Okay, so sorry, so additional definitions. So now let's start building a group action. So the input data for us would be a marked fan or a marked simplicial fan. And to this, we can associate several linear operators. So given a marked fan sigma, denote by sigma of 1 the set of rays. Then we can construct an R linear operator from R sigma 1 into V, which sends an element in the basis which corresponds to some ray to the marking on this ray. So rho of S is the vector we chose on array S. And also we can consider a homomorphism of abelian groups, which is sort of the same modulo the fact that we co-restrict to the abelian group, which is spanned by all markings or by all vectors on the rays of the fan. So far I have said nothing about like, I don't know, any sort of integral structure inside of the vector space. So in particular, this can be like a non-discrete subgroup of a vector space. Just like, I don't know, we took a bunch of vectors from the vector space. Maybe it's, I don't know, a subgroup in R, which is generated by 1 and the square root of 2. Why not? Okay. And moreover, if we have this, we can also associate to it the dual homomorphism, which goes from the topological dual of this group to, well, the topological dual of this group, but this group is discrete, so it's irrelevant. So it goes from, let's denote this group by gamma sigma, goes from gamma sigma dual to z sigma 1, just by applying linear duality. Okay.
The group on the right hand side isn't going to be discrete
Not necessarily.
because you could just have like enough like rays.
No, but also because you can have a dense subgroup in some like linear subspace. For example, as I said, you can generate something by like 1 and the square root of 2 on the line, and then the orbit of this group is like dense inside of the line. So yeah, this group is not necessarily discrete, but it is a topological Hausdorff abelian group. Okay, so let's consider an example again. So let's draw the fan which corresponds to CP2. So we have something inside of a two-dimensional space. Then we choose the following ray generators, and then the operators are of the following form. So this is a sigma, and then, well, it sends E1 to E1, E2 to, sorry, E0 to E1, E1 to E2, and E2 to minus E1, E2. And then you have the same homomorphism of abelian groups given by the same formulas. So now, for example, we can also consider the dual homomorphism, and the co-kernel of this dual homomorphism well, it's some quotient of z to the power of 3, and in fact, it's isomorphic to c. So this will become slightly more important later in the context of gradients, but also this allows us to build the group action. So we can take all homomorphisms of abelian groups from this co-kernel of this dual operator, which I will denote by L sigma, into just the complex torus. And this, because we have this projection, this naturally embeds it inside of C star to the power of 3. And in particular, this will be precisely the diagonal group action that defines CP2. So yeah, from this data we built, first we built this quasi-affine subvariety of the affine space, and then we built the group action using this additional data of like ray generators for some fan. Okay, and now this is sort of like the general construction of Taroyan varieties, because obviously you can take like a different fan. It has some like poset structure on its cones. This means that you have a simplicial complex, which means that you have like a subvariety like that. You can choose generators on the rays, which means that if at least you choose them in a way that this subgroup is discrete, this gives you some algebraic subgroup of the torus. Then you can take the quotient and you obtain a toric variety, like a general simplicial toric variety. So let me record that. following form. So you have sigma and embedded marked simplicial rational span. So I didn't define what rational means, but it precisely means this subgroup generated by ray generators is discrete. Then we have this algebraic quasi-torus. So it's maybe not connected, but still it's some sort of like abelian algebraic group, which is given by these homomorphisms. And then the toric variety is the quotient of the simplicial complex defined by cones of our fan by this group. And the quotient here can be understood in any sort of way you want. It can be like a categorical quotient that you glue piece by piece, or you can pick your favorite notion of a quotient. Extremely cool. Okay. So in particular, for CPN, we saw that you can do this using this fan that I drew here.
Sorry, what is K of sigma?
What is K of sigma? K of sigma is the simplicial complex, which has the same relations between faces as our fan has relations between cones.
In your
So-
definition of a simplicial complex, are the subsets ordered?
Yes.
So it's not, it's not.
No, but I mean, what's the difference? So like, I can explicitly tell you what that is. So the vertices, or like the set, is just the collection of one-dimensional cones. So the sigma one, and then the faces are just rays which span a cone in our fan.
Right.
So I don't know. I don't think that.
Oh, I see.
Okay.
Two, you have.
Yep.
Subfaces or multiply.
Yes. Because any face of a convex cone can be obtained, or at least if it's stronger convex, can be obtained by intersection with some hyperplane. Exactly.
Just say, how exactly does an element of this group act on something?
Oh, well, I mean, I sort of waved my hands a lot. So I said that this thing is projected upon by this Z sigma one, right? So if you take form of abelian groups from Z of sigma one into C star, you get the entire large torus. So using the fact that home is contravariant, you get an embedding of G sigma into the large torus. So because the large torus acts on the affine space, we automatically get the action of G sigma. Yeah, I mean, maybe it's not the best way to say it, but it is a way. Okay. So now let me move on to the second part, i.e. the description of automorphisms of complete simplicial toric varieties. So yeah, I will, of course, only sketch it, but I think the main reference for this theory and for like classical or parts of the stock that were known before is the paper of David Cox, which is called Homogeneous Coordinate Ring of Toric Varieties. Homogeneous coordinate rings. Yeah. So, description of automorphisms. complete. So the word complete was not featured before, except when I talked about the fan being complete. But you should think of completeness as compactness of dark varieties. So the fact that a fan is complete, i.e. it covers the whole space, means that the quotient like this is in fact a compact or a proper variety. Okay. So let me outline this approach. So that we sigma be a complete variety. So we have this sort of easy quasi-affine variety UK sigma. And G sigma acts upon it. So the strategy of Cox is to find regular automorphisms of UK sigma, which are equivariant with respect to G sigma. So that's the first part of the strategy. To achieve this, well, also to do many other things, he introduces this homogeneous ring or Cox ring for dark variety, which is some sort of algebraic gadget that captures this action, and by computing its automorphisms, we can compute equivariant automorphisms of this variety. So to do this, Cox introduces an algebraic gadget called the Cox ring, which is essentially just the coordinate ring of the affine space graded with L sigma, or like the group of characters of G sigma. So because CM has the action of G sigma, the coordinate ring naturally receives a gradient. And then the question is, can we compute like the graded automorphisms of this ring? Then the next step is to show that any automorphism of this sigma lifts to this link. And after that, it's sort of easy. You just have some sort of algebraic group which consists of graded automorphisms. So this thing, you determine that the kernel of this, I don't know, descent to V sigma is precisely the group G sigma, and then you're done. If like any automorphism can be lifted to this total space of this bundle, then this gives you the complete description of automorphisms of complete simplicial dark varieties. Okay, any questions about that? Okay. So let me illustrate the strategy on an example where we already know everything. So somehow the running theme of this entire thing is that somehow you know the answer for the projective space, and then you just want to build a theory that provides you with a lot of new examples that behave like exactly like the projective space, so you can write more papers. So in the case of the projective space, of course, we know all the automorphisms. So let sigma be the fan of CPN. So this kind of just a bunch of basis vectors and one vector pointing in the negative direction. Then this Cox ring, which is denoted by R sigma, is just the ring of polynomials in n+1 generators. And well, we saw that L sigma in that case was just Z. So the gradient group is just Z, Z graded. And then the degree of each variable is equal to 1. So great. Now it's sort of extremely easy to calculate graded automorphisms of this thing because, well, essentially you have generators in degree 1, and you want to know where the generators go. And this gives you just GL n+1 C. And then by this sort of thing that I didn't explain yet, you have an exact sequence like this. So this gives you algebraic automorphisms of CPM, and this is exactly PGL n+1. And then the point is that, well, we can do it for an arbitrary complete characterization. And moreover, I want to emphasize one thing here that, well, these are not just algebraic automorphisms. These are also homomorphic automorphisms. And in a sort of, I don't know, a slightly new and non-trivial part of this talk, we will see that actually this sort of fact that you can calculate homomorphic automorphisms by calculating algebraic automorphisms persists in other contexts as well, not just for these kinds of algebraic characteristics. Okay, so
But for any projective variety,
yes, but
homomorphic and
but more
homomorphisms would be the same.
That's true, but more generally, we will see that this holds without any assumption that you have a variety there. That like any equivariant automorphism of this kind of UK of sigma is actually algebraic, and that's sort of maybe one of the main novel things in this paper. Okay, so yeah, so now let's move on to this notion of generalized fans and Cox rings. So this was like as much as I was willing to say about the classical theory, because as we'll see in a moment, there is sort of a very straightforward generalization that has all the same features, but it is more suitable for our purposes. So I will just introduce that and then explain how it works in that context. Okay. So part 3, generalized fans and their Cox rings. So yes, so in the previous part, I sort of said that let's call something an embedded fan, which sort of hinted at the possibility that the fan can be non-embedded. So let me give the following abstract definition. So consider a quadruple as KV rho, where this is a finite set. This is a simplicial complex on S. This is a real vector space. And this thing is a map from S to V. So this sort of completely abstracts away from any idea that you have like actual clones and actual vector space, and you just want to like remember the combinatorial structure plus the data of like ray generators. And we don't impose any sort of conditions on like anything here. Okay, so this is the generalized fan. This is the generalized fan. And of course, we have the same pair of operators associated to it. And we have the homomorphism of abelian groups too. So sigma. And then we have a dual homomorphism, which goes from the topological dual so it's just all all continuous homomorphisms from gamma of sigma into Z with discrete topology. Okay. And also we have this grazing group L sigma, which is Z of S modulo gamma sigma dual. And this gives rise to some sort of algebraic group. Okay. So we have that. And now, so first of all, let me make the following trivial observation. So if you have a marked fan, a marked embedded fan, this naturally gives you like a generalized fan just by considering the appropriate simplicial complex, and the marking gives us this map rho. So let me give the following example / construction. So one of the main features of this new definition is that unlike in the case of like usual fans, we don't really care about linear maps that we use to transform our fans. So like in the usual toric geometry setting, somehow it is not true that if you take an arbitrary linear map, an image of a fan will be again a fan. But here it's sort of completely irrelevant. We can allow ourselves to like project everything to, I don't know, to a single point or whatever. So let sigma equal to S0 be a generalized fan. And assume that you have some sort of linear operator that goes from V to W. Then you can define a push forward generalized fan like this. So in particular, given any subspace of V, we can project our fan along the subspace. And this will be canonically a generalized fan with the vector space being the quotient space. And moreover, we can observe, this is once again completely tautologous, that any generalized fan is a push forward of an embedded fan. So we'll always have an embedded fan like this. And then this pushes forward to an arbitrary other fan. Just using the map raw. Well, I don't know how correct. Oh, yeah. And so, in some sense, this is like the abstract Fox construction for generalized fans. So let me maybe make it a bit more precise. So a morphism of generalized fans is just a morphism of simplicial complexes plus a linear map between associated vector spaces that commutes with appropriate maps. So sigma to sigma prime is a pair of maps, one combinatorial, which goes from K to K prime, and one linear, which goes from V to V prime, such that they commute rho prime. Okay. So now the question is, why would we need something like this? So in the previous example, the goal was sort of to classify all algebraic varieties that you can obtain as quotients of some quasi-affine subvarieties. So now a natural question is, well, we have some sort of combinatorial gadget, what it corresponds to geometrically. And yeah, and the answer is that we should think of it as corresponding to some sort of toric stacks. So here, as you can see, well, everything that we did for regular fans proceeds for generalized fans just as well. We have some sort of algebraic group. We have some sort of quasi-affine subvariety. And then, well, we can take the quotient stack. Maybe it's not a variety, but who cares? Okay. So now let me define Fox rings of generalized fans. So let's sigma be a generalized fan. Then its Fox ring, rather unimaginatively, is just a polynomial ring on generators corresponding to the elements of S, graded by L sigma and L of sigma. And of course, so if you have like a basis vector here, which corresponds to a variable, to determine like the gradient of the variable, you just project it to L of sigma, and you have the gradient. So now let me give you the following definition. So let sigma be again a generalized fan, then a rationalization of sigma is the universal fan sigma underline, which lies under sigma with respect to morphisms of fans, such that it is rational. It's rational, i.e., gamma sigma is discrete. And the way you construct it is sort of very simple. So if you have sigma, you have this operator A sigma, and this operator A sigma has a kernel. It's some real subspace. So then you can just take the smallest rationally generated subspace, which contains this one, and then you take the quotient with respect to this subspace. And this produces for you a rational generalized fan. Okay. So I will just end with the following observation, that the Cox ring of a generalized fan canonically is the same as the Cox ring of its rationalization. The reason being that this gradient group actually depended on the topological dual of gamma sigma, which means that if gamma sigma was somehow non-discrete, it all was lost under topological duality. So this thing only depends on the rationalization of your fan. Okay, I think it's a good time to take a break. And after that, we'll continue. Okay, so let's resume. Yeah, so before the break, we defined what is the Cox ring of a generalized fan. So now I'm going to talk in a bit more detail about structure. So let's function. So let sigma be a generalized fan, and we define L of sigma as a co-kernel this operator, and we can split S into a union, disjoint union of some number of subsets according to the gradient. So each element of S or each generator which corresponds to an element of S has a gradient, and we split the set S according to like the equivalence relation having the same gradient. So denote by, so in particular, for example, for the projective space, S was like split into a single subset of elements of variables which had gradient 1. So denote by alpha 1, alpha t, these gradients. And now each graded component of the Cox ring splits into direct sum. So you have generators of variables and decomposable monomials. And sort of the point is that you only care about the generators if you want to calculate graded automorphisms. And moreover, we have the following proposition, which is essentially, I think, due to Fulton. So yeah, I mean, maybe let me make this traditional detour that the notion of the Cox ring was actually defined by many people before and around Cox. And I don't think that before Cox it was graded, but in principle it was studied already in some literature on Taroyan varieties. In particular, Fulton proved that you can identify monomial bases of like components of the Cox ring, or just, I don't know, identify monomial bases, additive monomial bases of the Cox ring with a certain collection of like lattice points. So if sigma is a generalized fan and sigma bar is its rationalization, then we can define set P alpha. So rationalization with, of course, the same set and simplicial complex with vector space W and map raw bar. So P alpha is the collection of functions on W such that T rho of S is greater than or equal to minus alpha S. So because we're dealing with complete fans, this is some sort of like, I'm sorry, it's not visible. Yeah. Okay. So regardless, because we're dealing with complete fans, I'm not going to delve into too much detail on this, but the point is that because the fan is complete, this condition ensures that this is a compact region. So this is some sort of like a polyhedron inside of W dual. And the point is that this thing is a compact region. This is very important. This is, in some sense, essentially where sort of the compactness of the quotient variety or quotient stack comes in. So I define this, and I will have to write the statement of the propositions over here. So the claim is that gamma sigma dual intersected with P alpha bijectively corresponds to the monomial basis of R sigma alpha. So this is some sort of lattice. This is a compact region, and this shows that this is a finite dimensional C space. So yeah, and in particular, of course, you can define a Cox ring for a non-complete fan too, but then P alpha won't be compact. This statement will still hold, but you'll just have like some sort of like infinite dimensional.
It's now about these elements. So we're splitting S up, like I can identify elements of S by a row with things which live in the vector space. The vector space is acted on by this group, right?
No. In this case, I'm identifying S with functions on that vector space because I'm identifying elements of S with variables. But regardless, like you can identify elements of S with basis vectors in ZS, and then they project into L sigma just canonically. And this gives us some sort of gradient because, well, you have a class in L sigma corresponding to each element of S. Okay. All right. So now, let me give you the main proposition about automorphisms of, or graded automorphisms of Cox rings. Which, once again, should be thought of as a straightforward generalization of what you have for Pn. So first of all, let me define for the set S read as collection of all S small in S such that S belong to sigma for some sigma. Okay. So S minus the ghost vertices. Then group of graded automorphisms are sigma, which is denoted just by what G sigma. Well, it's a linear algebraic group, and we can explicitly describe its unipotent radical, like a reductive subgroup that together with this unipotent radical generates the whole group. And moreover, later I'll tell something about describing the roots of this group. So The first statement is that G sigma is a linear algebraic group of dimension so we're taking sum over all these components of S, of cardinalities of SIs, and dimensions as C vector spaces of the components of the Cox ring, which correspond to these gradients, plus the number of ghost vertices. The second statement is that the unipotent radical are sigma of what G sigma is isomorphic as an algebraic variety to the affine space of dimension again, we take the sum over these components of the dimensions of the components of the Cox ring minus cardinalities of SIs. Additionally, we have a reductive subgroup which is just a product of GLs on the spaces of indecomposable monomials in each graded component times the torus on ghost vertices. And finally, that, well, you have this reductive group, you have the unipotent radical, and then you have a semi-direct product decomposition of what? Okay. So, like, let me maybe comment a bit on what is happening here. So, if you look at this, you see that the total dimension is obviously just the sum of the dimension of the reductive part and the unipotent radical. For the unipotent radical, you basically have something that should be thought of as like upper triangular matrices, because this roughly corresponds to, like, well, not roughly, maybe in some sense precisely corresponds to the dimension of like the graded component minus the dimension of the space of indecomposable monomials. So this is sort of the thing that depends only on these. Well, it's like an upper triangular matrix. And then this part precisely corresponds to just all linear transformations of the space of like indecomposable monomials, which is the part that is missing here. And then also we have this torus, and somehow the point is that these ghost vertices are sort of irrelevant for the classification, because they correspond to the part of the Cox ring which is graded with like Z, with the entire Z, not the M. And so in particular, it means that any graded automorphism should just be like a C star thing.
We're calculating automorphisms of this like stack.
Oh, no, we're calculating automorphisms of a graded ring.
Of the Cox ring. So there's no claim that like the Cox ring is like
Not yet.
design.
Not yet, no. There is no claim like this yet. Okay. Well. Yeah, so now I formulated this. The claim is that if you read the paper of Cox, you can prove this yourself. This is like an extremely similar argument to what Cox does. Nothing particularly new here. Now let me describe something. Let me describe root subgroups of this algebraic group. Okay. So we have the following definition: the set of de Mazur roots. De Mazur roots of a generalized fan is a collection of all m's in this sigma dual, such that there exists an S small inside of S large, such that if we pair like this, we get 1, and for everything else, we get something which is less than or equal to 0. So the idea is that this somehow should describe combinatorially some sort of like one parametric families of algebraic automorphisms of UK. So let me describe how we get a one parametric family of automorphisms from a root like this. So instruction, assume that you have a root ms which corresponds to some element s of s. Then we have a one parametric algebraic group, GA, which acts on CS, and it acts as follows. So essentially it changes a single coordinate, and the single coordinate is changed by taking a sum. So lambda is the coefficient of the one parametric family, or the parameter of the family, and then this is some sort of monomial, which is like meaningful because we have this condition. And the claim is that the roots of that group are precisely, well, the ones that correspond to these guys. So let's consider an example. So in our favorite case of CP2, our fan looks like this. And then the condition that the product is equal to 1 gives us 3 lines like this. And then the condition that something is non-positive gives us hyperplanes. Half spaces like this. And the claim is that we have the following roots. So we have a root like this, a root like this, a root like this, a root like this, and two roots like this. This sort of corresponds to like the root system that you expect. And in particular, like if we do this calculation, we would just see that we get, for example, for m equal to e1. So for this root, we just get L z1 to the power of 0, z2, z1, z2. this is the one parametric family. And then the same thing, for example, happens for E1 minus C2. So anyhow, these are just shifts, like shifts of the affine space given by things like that. Okay. Any questions about this? Okay, so now let's move on from Cox rings automorphisms to actual automorphisms of some geometric objects. So I want to just make a small comment here that you can quite easily observe that this construction of a Cox ring, despite the fact that we built it from a generalized fan, in fact, only considered like a group and like the number of vertices essentially. So it was just like an action of a group on the affine space. So in particular, this kind of thing doesn't know anything about this quasi-affine subvariety or anything like that. So it just turns out that in like classical toric case, we don't need any additional information to relate these automorphisms of the Cox ring with automorphisms of the toric variety, but this is not necessarily the case here. Okay. So Cox rings morphisms to automorphisms Cox construction. So claim is the following. So let sigma be a complete generalized fan. Then given any holomorphic automorphism of U sigma normalizing G sigma is algebraic. So let me maybe say a few words about this. So this should be thought of as some sort of like equivariant Gaga type statement that like if you have a proper quotient, whether it's like an algebraic variety or an algebraic stack, the automorphisms which are equivariant with respect to this group action or the automorphisms on the presentation which descend to the stack are necessarily algebraic. And in this case, you can give like a completely elementary proof of this fact. So in the end, it reduces to some like actual just explicit calculation with power series. So you can just like write down the power series of the automorphism, and then because of compactness, you can show what. Okay, let me do this argument. So if your fan is complete, whether it's an actual embedded fan or you just know that like the images of like semigroups which correspond to faces of your simplicial complex cover everything, there exists a strictly positive combination of rho S's that is zero. That's just a feature of like a complete fan. And then how you should think about this positive combination of rho S's which is zero, you should think of it as a vector which points inwards in this orthant given by like the set S. And so now if you write down the power series for the automorphism, it will turn out that the all non-zero coefficients of the power series should lie inside of an intersection of some hyperplane normal to this vector with this orthont, which, because this vector has purely positive coordinates, is necessarily compact. So in fact, this power series is a polynomial. And that's like a very, very simple argument to prove something like Kaga in this case. Okay. So that was an argument that allowed us to say that actually when studying like holomorphic automorphisms, we can just as easily study algebraic automorphisms. But now let me relate algebraic, like just automorphisms of the Cox ring with equivariant automorphisms of the Cox construction. So let's denote by odd tilde of sigma the group of the connected component of the group of equivariant automorphisms of the Cox construction, or if you want, the group of automorphisms of the Cox construction which centralize G sigma instead of normalizing it. Then the claim is that this is a subgroup inside of odd G sigma, which is spanned by C star to the power of S and group subgroups which preserve U of sigma. So as I was saying, this definition of root subgroups, for example, only depended on like the set S and the way we map it into the vector space. But it didn't know anything about this subvariety. So there is actually some non-trivial, in general, there is a non-trivial condition which ensures that these root subgroups preserve U sigma. And you can formulate it in purely combinatorial terms in some sort of like, I don't know, cone, like there exists some cone which contains some other cone. And yeah, that's how we formulate it.
And here by the tilde sigma, you actually mean like automorphisms in the stack, like
automorphisms of U sigma. Yeah, it's automorphisms of the presentation of a stack. So yeah, there is something that needs to be checked here. Okay, and also I want to note that if sigma came from an embedded fan, so like it actually corresponded to some like actual torque variety, this condition is void. So somehow the fact that you have like this nice fan ensures that every root subgroup preserves this algebraic variety. Okay. So now let me say a few words about applications of this whole thing. Yeah, and also maybe let me mention that the group of components of odd tilde sigma can also be determined in terms of symmetries of the fan. So, odd tilde sigma mod So the sigma comes from symmetrics. So you can also completely describe what that is.
You know the code image? This,
It's like connected component. What do you mean? Code dimension is 0.
inside of Lodge. You're saying this is a subregion.
Oh, inside of OG, well, I mean, no, it really depends on the combinatorics of your fan, if you want. Because yeah, no, it really depends on the combinatorics, because I can essentially I can do something like I will take an empty simplicial complex and I will take something which corresponded to like CPN, like rho which corresponded to CPN. Then I will have like a whole bunch of root subgroups, like a lot of them, but none of them will preserve like C star to the power of n+1 inside of Cn+1. So it really has to do with some particular combinatorics of your fan. But of course, like given a fan, it's pretty easy to determine how many you have. Okay. So what are actual applications of this? So I promised something about automorphisms of complex manifolds. So application number 1, holomorphic automorphisms of certain non-algebraic complex manifolds. So first, let me give you like a conceptual picture of what is happening and what type of manifolds we're considering. So we have this U sigma, and in principle, like we have the action of the large torus on U sigma. In principle, you can just consider arbitrary like complex Lie subgroups of the torus, not necessarily algebraic. And the quotients now will not necessarily be algebraic varieties or like algebraic stacks. So you can consider an action of some complex Lie subgroup inside of C star to the power of S. And for it to be related to our toric stack, I would additionally require that H sigma is a real form of G sigma. So this is slightly weird. So H sigma itself is a complex Lie group, but there is no problem in complexifying it again and obtaining G sigma. So like it's a group of half dimension of G sigma. Then the quotient here will be what is called complex moment angle manifold. And here we have this either a toric stack or a toric variety V sigma. And here you have G sigma mod H sigma. So in some sense, you know automorphisms here, you want to know automorphisms here. And before I tell you the reason why you can use this diagram to determine automorphisms here, let me just give you a couple of examples of what this Z sigma can be. So one of the first, maybe most famous examples of non-Kähler complex manifolds are these Hopf manifolds. So Hopf manifold is topologically a product of a circle and an odd dimensional sphere, which can be obtained from like Cn without the origin by taking a quotient with respect to some action of the group Z. In our case, we want it to be an action by diagonal matrices. But it also admits another presentation. You can increase the dimension of your space by 1, and instead try to mod out by an action of C. And then, well, this fits into this sort of setup. So in particular, you can obtain Hopf manifolds like this. Or there is a straightforward generalization of this called manifolds called Calabi-Ekman manifolds. So these are products of 2 odd-dimensional spheres, which can be obtained in a similar way. You take like a product of 2 copies of like C plus 1 without the origin times CQ plus 1 without the origin, and then you mod out by the action of C. And the point is that these guys fiber over products of projective spaces. Or if the data gives you some like irrational fan, they fiber over some toric stack, which is not necessarily an algebraic variety, but still it has a structure of a toric stack. So these are some examples, and now let me apply this sort of theory to calculate their automorphisms. So let me first make some claims that follow from the work of Ishida on classifying like complex manifolds with certain types of torus actions. So first corollary of this is that if you have a homomorphic automorphism of Z sigma, then it necessarily preserves the orbit foliation of this quotient group. The reason for this being that this orbit foliation has sort of an intrinsic characterization in terms of the complex structure on the manifold. So you can define like a maximal torus acting on your manifold, and then using the Lie algebra of that torus, you can define this orbit foliation. So any automorphism here is equivariant with respect to G sigma mod H sigma action. So in particular, it descends to the toric stack. Second, for any automorphism psi inside of holomorphic automorphisms, if so descends to the sigma descent homomorphism will be denoted by pi. So if pi psi is equal to identity on the sigma, then psi belongs to G sigma mod H sigma. The reason for this being some sort of like basically like compactness argument about the base. So there can't be like a non-trivial transformation that preserves the fibers of this projection. And because well, essentially like the fibers of this are always either like the additive group or like a compact torus, or a product of an additive group and the compact torus, which means that we would need to have like a non-trivial function from something compact into like a torus or the affine space, and then it's like a Liouville type theorem that shows you that you don't have any non-constant automorphisms. And then from this, we derive the following result. So we have presentation like this, where here I need to additionally require that I'm only taking those automorphisms of the Cox construction which preserve H sigma inside of G sigma. So this doesn't have any effect on the connected component because it centralizes G sigma. So in particular, it centralizes H sigma. But there might be some like automorphisms in the component group that I have to throw out to like get this thing. And in particular for Calabi-Ekman or Hopf manifolds, this yields the following. So this thing, just because it is the same essentially calculations for the projective space, will be GL T plus 1 times GL Q plus 1. Then here we have C, and then the quotient is the automorphism group of Calabi-Ekman manifold. Okay. So let me now tell you some caveats that are still remaining. So some of them are conceptual, some of them are just a matter of well, I don't know, writing a paper. So I want to sort of precisely specialize what is actually known here and what is not. So like in this paper I'm basing the stock on, it is proved that if the fan is rational, this is true because the base is actually an actual toric variety. So we have a lifting statement for toric varieties, which is needed for this. So caveats. So number one, the case of sticky base, and this is not a conceptual difficulty because proving a Lifton statement is sort of easy. We know what is the cohomology of the base. There exists a calculation of this, and essentially to prove a Lifton statement, you need to show that some cohomology class is fixed, and this is done similarly to how it's done for toric varieties. You just need to like write it down, or I don't know, I need to write it down probably. And so this is non-conceptual, but still, I don't want to sort of mislead you into believing that something is proved when it's not. So another very slight difficulty is that in general, this thing might not be connected because, well, for toric varieties, G sigma can be some sort of like a torus times a cyclic group or a product of cyclic groups. But this is also sort of very, very, very simple to fix. So this thing admits an exact representation inside of like the Lie algebra of the connected component, and then you can once again use the canonicity of this thing to deal with this thing. And finally, this is, I think, sort of more open. In principle, like by arguments similar to this one, you can prove that, in fact, any equivariant automorphism of the Cox construction with respect to an arbitrary subgroup of the torus, such that the quotient is compact, is algebraic. So in fact, the thing that we dealt with, like algebraic subgroups, was completely irrelevant. You only need to know that, like, if you take like the closure in classical topology, and if the quotient is compact, then any equivariant automorphism is algebraic. But the question that is, I guess, sort of open is it true that if you take UK modulo an arbitrary subgroup with this property inside of C star M, its automorphisms are described by automorphisms of the Cox construction. Okay, so I think that's it, and I have 5 minutes for questions. Thank you so much. Yes.
So, you're looking at automorphisms of some algebraic stack.
For example, yes,
Okay, so.
or complex analytic stack.
So, like algebraic stacks, differential stacks form a five category, like a weak two category.
Oh yeah, yeah.
So
yeah.
look at the automorphism. This thing, you're going to get some.
No. Actually, yes. Sorry, I wanted to say this, but then when I was preparing the talk, I completely forgot about this. Of course, this, and I think that this was known before in some sort of like, there is this paper about Stakey fans. So it's a sort of very mild case of this problem of the setup. So you can actually promote everything here to like the sort of two group thingy, and the answer would be that, well, like the whatever crossed module that represents your two group is precisely, well, this thing. So, well, yeah, that's the answer. So it's yeah. But thank you for the question. Or
Questions? Grisha again?
Thank you.